Hi, in this video, we're going to take a look at evaluating our regression supervised learning models after we've built them. Okay, so something that is critically important for us before we launch a model is we need to convince ourselves, convince our stakeholders that our model is safe to buy. Our model is good for the solution that it's being applied to. Now, there's a bunch of different ways to evaluate this. Here, I'm going to go over some major, more common ones to go about it. Normally, when you're working through supervised learning and learning about it, you learn about all these different model structures, and then you start talking about model quality. I want to do model quality first because model quality is far more important than the actual structure of your model. Something I want to emphasize is that parameters and model structure are not as important as other aspects of the supervised learning aspect. Your data quality is number one. Data prep is a big aspect, but just also going through and making sure, do I have a good model? Or is my model good enough? Is going to be a super important aspect to our project. All right, so I'm going to do a simple linear regression, not simple, so a multiple linear regression model with the house prices advanced regression techniques data set from Kaggle. And we're going to go through and just talk about different ways to check to see, do I have a good model? Now, all of these different metrics that we're going to look at have strengths and weaknesses. And what we're going to end up doing in real life is that I don't just look at these on their own independently. I look at these and really compare them to other models. So when I'm working on a project, I'm going to build multiple random forest models. I'm going to build multiple stochastic gradient boosting models. I'm going to build multiple k nearest neighbors model, multiple linear regression models, and I want to compare them. I want to see which one is the best. And from a small pool, I'm going to select one, and then I'm also going to use my train, validation, and test statistics to evaluate, is it good enough for my project? And so let's go ahead and get into it. All right, so first thing I'm going to do is, if you've watched my videos, you know I do this every time. I prepare my workspace. I set it up so I don't get a whole lot of digits printed out. I don't want too many. Side pen, larger number, means that R tries not to use scientific notation. Warn suppresses warnings. So when I was working through the script for this video, I looked at the warnings. I did everything step by step. I'm aware of what warnings we spit out. I do some things that the tidyverse doesn't like frequently, specifically with character strings. For I mix standard and non-standard evaluation, and that'll throw a bunch of errors with depreciated functions and stuff like that. I go ahead and just use depreciated functions because they're there, they're good, they work, but they throw warnings. Here, I'm just making sure I don't have any junk in my workspace, that any artifacts that R could think is something else. And I'm using the McGritter package for piping. Now, previously, I downloaded the house prices data set from Kaggle, and then a previous video, I went through and did data prep. If you remember, I went through, and for my numeric variables, I considered Box-Cox transformation, I considered Yo-Johnson, I considered exponential transform, ended up not using that one at all, and then not transforming the numerics at all. And that's how I treat my numerics. For my ordinal and categorical predictor variables, I chose to do binary bending, as I bend it into two levels. I find that this is a good choice for initial runs as I work through the data process. I will build some initial models, and then when I start feeling comfortable, feel like I've got a better idea of what I'm going to do and what I'm not going to do, I'll go back, and the predictor variables that I'm going to use that are categorical, I'll reevaluate how I'm bending them and then double check it. The fewer predictor variables I have, the less of a risk I'm exposing myself to overfitting. So during this initial phase, I keep everything down to dummy variables just being one column for categorical variables. This is very, very coarse binning, but I think it's good for first runs, especially when I have a lot of predictor variables to work with. All right, so I'm going to read in my data, and here C represents a character string, and n represents a numeric on this one. You'll notice we don't have any dates. I don't have anything as factors. I prefer to keep things as character strings over factors if the R functions will accept it. Now I'm going to create a column that is for the train and validation. So in this data set, we have a train and we have a test set. Well, this was from a Kaggle competition. So that test set holdout data set, I don't know the true values for. Since I don't know the true values for it, I can't use it. And so I'm just completely treating that as a scoring set, and I'm just leaving it alone. So I still need to do my train, test, validation process. Train and validation are the more important ones. Train, I'm building the data. Validation, I'm using metrics to decide which model is best. So I'm going to go ahead and create a train validation split. And to do that, I am using a random number generation. And standard uniform is being generated here for the number of rows in my data set. If the random number is greater than 0.5, then it's validation. Otherwise, it's a train. Well, it'll be tested if the data set is test. And then, all right, so I could actually get rid of this as junk code. Then I'm going to fit the model. All right, so I went ahead and I took all the predictor variables in the data set and I ran forward selection, backwards elimination, and forward back. This was the model that had the fewest predictor variables, which was the backwards elimination. And so I chose to use this one. And then remember that when I build my data set, I only want to use my training data for building. And so you'll notice I'm filtering out so that I only have the training data. And notice I'm using the formula notation for this. Some R functions will accept formula notation, some will not. This one will take the formula aspects. All right, and so now that I have a linear model built that I can start evaluating, I'm going to go ahead and run predictions. And so I'm going to take my data, I'm going to put it into the model I just fit. And using the predict function, here I have the model I just fit. I'm saying to do this for every single row of data, figure out what is the modeled value. So simultaneously, I've got my train, my validation, and my test set model values in one shot. Very nice. And then to get the residuals for each of these, I'm going to do some subtraction. And on the test set, it's going to be NA because there's no actual value on there. Now, notice how I define my residual. I say the residual, different textbooks do different things, but I say the residual is the predicted value minus the true value. Why do I do that? Well, in this order, instead of reversing it, if my residual is positive, I know that the predicted value is too big. Positive is too big. Negative means my predicted value is too small. I like to have that correspondence. Other functions, other people define it in the reverse order. Just check out what's going on so you know what's up. All right, so now let's actually talk about the metrics for that. These are the most common metrics. You can find tons and tons of different ways to evaluate model quality. I'm going over the big ones. If you look at the help documentation for scikit-learn's loss functions, that gives you other ones that you can also use, especially for the classification models. Here, I'm just going over the ones that were on the top of my head, the ones I've used that work the most. So the first one is the mean squared error. This has a very strong theoretical aspect in linear regression. So classically trained statisticians like this a lot. And because statisticians have taught people to use mean squared error so often, this has become very common to be used in supervised learning in general. Now, in this formula, you notice I'm squaring the residual. That something squares is always positive or zero. Then I'm adding it up. Then I'm dividing by n. So it's the mean squared error. Now, if you'll notice, the units for this are squared. So if my original model was in dollars, my mean squared error is in dollars squared. So it's a harder connection between the actual original values my target variable and my MSE. And so dollars squared doesn't really make a whole lot of sense. So frequently we use root mean squared errors where we just take the square root of our mean squared error. And so boom, we just take the square root. So now if my original target variable is in dollars, my root mean squares error is also in dollars. So that's nice. Makes it easier to interpret. But honestly, when I talk to my stakeholders, I still don't like this. For me personally, it's hard for me to really talk about what is the root mean squared error. Think about the mathematics of that. I'm squaring the error, adding it, and then I'm taking an average, all right? And then I'm taking a square root. So I've got squaring, average, square root. That's a little bit much for people who don't have a strong math background. So I prefer to use the mean absolute error when I talk to my clients. So specifically the ones that have a weaker, math and statistics background. If they've got, if I'm talking to my boss, if I'm talking to my coworkers, mean squared error, boom, whatever, whatever works for them. But when I talk to my stakeholders, my decision makers, I say average error. I just say average error, period, instead of saying mean absolute error. So here in the mean absolute error, I take the absolute value of the error, then I take the average. All right, so that's a little bit easier for people to understand because if I say error, if it's 5 off, people frequently don't really care if it's above or below. And then if I just say average error, people tend to accept that better. So I like this better for the purpose of speaking with stakeholders. Now, if I'm in a regression point of view and I'm doing a theory aspect, I'm going to be using mean squared error 100%. Now, something to consider about these two or these three when you are doing your loss function. So let's say we're using scikit-learn and we have to specify what our loss function is, or we could be doing this in R, a lot of different ways. So if I do squaring, when I square a number that is between -1 and 1, strictly between them, the squared value gets smaller. And if I square a number that's greater than 1 in magnitude, the squared value is bigger. Okay, so why does that matter to us? Well, what's going to end up happening is that mean squared error, if I'm using that as a measurement of a fit, or as a way to fit a model, so if I'm optimizing for mean squared errors, mean squared error is going to work harder to avoid big errors, and it will accept a lot of small errors, to avoid one big one. Now, mean absolute error, what it's going to do is it's going to try to be a little bit more even about things. And so if I had, imagine I have a whole bunch of little errors and one big error. Mean absolute error isn't going to sacrifice the bunch of little ones for one big error. It's going to take a more balanced approach. While mean squared error is going to avoid that big one a lot more. If I was to change this to, let's say, the absolute value cubed, or the fourth power, absolute value to the power of 5, absolute value to the power of 6, and so on, the larger that exponent I put on there, the more in the optimization process, we would be trying to avoid large errors. In doing so, we would be sacrificing smaller errors. So what would end up happening is we could pull, let's say I put 10 instead of 2. What would happen is big errors would come down, but then a lot of little errors would get bigger. And so it would, we would be, for a lot of little data points that would be like relatively close normally, they'll start shifting away just so I can get this one data point to fit better. Mean absolute error tends to take a more balanced approach. In the project I'm currently working on, I was using mean absolute error, but then I had problems with the extreme values out in the far left and far right. And so after looking at it, using the techniques in this video, by the way, I would use the techniques in this video, the vision tile plots, to know where the error was. And I said, hey, I have a problem in the tails I switched from mean absolute error to mean squared error for my optimization. And so, how you choose to measure your model has an impact on the results. All right, so here's what I'm going to do. So we talked about MSE, mean absolute error, and root mean squared error. And I'm just going to print these out by train and validation statistics. So here I've got for my training set. So on the data that the model was fitted on, here's the mean squared error. Here on the training set, here is the root mean squared error. And here is the mean absolute error. And so here's, and we can see, the difference. And it ends up just by happenstance, validation looks better than test. Don't expect it to be that way in the future. All right, so in general, your validation statistics will look worse than your train statistics, and your test statistics will look worse than validation, and score will look worse than test in general. If you don't see that, throw a red flag, start digging deeper into your modeling. All right. And so now something to be mindful of is all three of these are on different scales. How will I actually use these in real life? Well, if I'm talking to people who are comfortable with these statistics, I can tell them, here's my average error, here's my root mean squared error, and it gives them an idea of accuracy on their own. How we're going to use it more often, though, I'm going to build multiple models. If I build 10 different models, I need to pick a few to dig in deeper to have like candidates for the actual models I'm going to launch. And so what we're going to do, we're going to use our validation statistic to choose which model we're going to run. And then we're going to use our test set to actually get an honest estimate, even though it's still optimistic, of how our model will perform in the future. Now, you always want to get your training statistics also, because the difference between our train and validation statistics are our way of measuring, have I overfitted my model? And this is in those models I was just talking about. I have mild overfitting. I know it, but I feel like it's okay given the constraints of other constraints of the project. And I'm using train and validation to catch that. All right, yeah, so here, we can see that the validation statistics are better than training. That is a fluke. That isn't going to happen most of the time. Linear regression tends to be a model that what I get during training and validation tends to be what I get close to it when I actually score the real data. When I build models that are more flexible, you're more likely to have a big gap between what you saw during your building when you were building the model and when you actually run your model on real life data. All right, the next thing I want to talk about is looking at the correlation between your target variable and your predicted variable. And on this one, we always want to use Pearson correlation on this. So this is the classic correlation. If you hear correlation and no one says a name with it, it's Pearson correlation. And so here we have a 0.93 correlation between our model values and in our actual target variable. I did not split this out by train validation. I should have. I forgot, but at work, real life, I would have two correlations, one for train, one for test. Now I think about it, I forgot to do that across the board. Now, Kaiki's information criterion, what this does, this tries to model how well does the model fit along with how many parameters I have, how complicated of a model. And this 2K, this is representing how complex my model is. The more parameters I have estimated, the more complicated my model is. Over here, this is the estimated likelihood of our model data combination. Not all model structures have a function to evaluate this. Linear regression, we have it. Tree models, we have it. Generally the simpler models. When we get into the more complicated situations, we won't have AIC or BIC to work with. And so what we want to see is we want AIC and BIC to be at the least value possible. So least is better, greater is worse. Most of the time, some packages in R, like B and learn, multiplies this by a negative sign. And when we do that, there's problems with it. So, or not problems, but we just have to know that it's reversed. So AIC is considering how complicated the model I have and how well does it fit, and I want the least value possible. Now, the BIC, Bayesian information criteria, you'll notice that it's the same formula. I have K as the number of parameters, but now I have log of the number of data points I have. And so what is going to happen here is that this is going to put much more emphasis on simpler models. And so this is a much bigger penalty. Now, I'm still going to be wanting the least value possible when I compare multiple models together. Now, next thing I want to talk about is visualizing your regression models. Now, if we're digging into like regression by multiple linear regression by itself, it has way more visualizations, way more statistics that we can use. I'm not going to be digging into them. I'm just going into ones that apply to every single regression model possible, regardless of the structure. And so the first one is just a scatter plot of my target variable by the predicted variable. All right, so here's that scatter plot. The vertical axis is my target variable. The horizontal axis is the predicted values. If I had a perfect model, every single data point would be sitting on this line. This is the line of best fit between the predicted value and the box-cox. And so ideally, I would see this as zero-intercept y equals x line. That's what I would like to see for this. If everything was perfect, it won't always be. Now, something you'll notice I also did was I colored the points by their value for the target variable. And so I set this up so that approximately each color has a third of the data points. This helps me check to see where are points clumped up, where are they spread out. You'll notice that visually, I have like a smaller area for the red than I do for blue or green. But I know that blue, red, and green all have approximately the same number of data points. That tells me that I have points clumped up on top of each other here. So that helps me figure out what's going on. Now, the next one is a vigentile or decile plot. What we're going to do here is I'm going to take my target variable and I'm going to bin it into 5% or 10% groups. I could also do 1%, whatever percentage you want. Usually we do something that will divide 100. So here I've got 20 groups. Could also do 10 groups, 100 groups. 2 if you wanted to. At work we use vigentile plots, so I'm going to do a vigentile plot here. But just do whatever your stakeholders are comfortable with. And what we're going to do is in each of those bins. So here, this is a bin of the target variable. I'm going to take all the rows of data that have target variable in this bin. I'm going to take the average of the target variable and the average of the predicted value. And you can see that I've done this for all 20 of these little buckets. And so what I want to see, ideally, if I had the perfect model, the modeled line would be directly on top of the target variable line. And so this isn't an exact perfect match, like the scatter plot. Each time I have y value and x value, they match perfectly. Here, I've got the x value and the it corresponds to the bin. The y values are averages. And so here, I'm taking the average in a bucket for the target variable. I'm taking average within the bucket of the predicted values. And I'm checking to see, are the averages close? Now, typically, you're going to see far to the left and far to the right. They're not going to line up perfectly because of just outlier aspects. And and this is no exception to this. We can see that the model does not go as extreme as the actual data does. And that's usually what we actually want, because in real life data, we're going to have some weird anomalies, some weird outliers. They're going to pull the far left and far right buckets up and down in the plot. And so we want to see that our predicted values like don't really reach that far out. That's okay. If I saw a huge drastic difference, then that can be a problem. Now, something that's nice about this, if I had, let's say, two other models I'm considering, I could plot all three models onto the vision tile plot. And I do the same scheme where I bin by the target variable, then I take averages for each of the models and then plot the line. And this is a way for us to compare multiple models on the same visualization. Now, something I noticed here in my validation set, you'll notice that there's a bit of a difference here. And so one of the reasons why I like this plot is that when my model isn't good enough, my vision tile plot can at least say, hey, in this region, your model isn't performing as well. Like for this target variable value in this range of 5% of your data, it's not performing as well. I have a direction to go in to try and figure out, what's going on. Maybe I've got outliers. Maybe there's anomalies. Maybe I've got polluted data. Maybe maybe the model just isn't dealing with that type of that region of the higher dimensional space very well. All right, now the next one is to set up box plots. So the idea here is very similar to what we have, but now I want to use box plots. So notice that here in these plots, I'm just dealing with averages. I took the average within each bucket. Buckets are defined by the target variable. Now here I'm going to play the same game that I'm taking buckets of the target variable, and then instead of just doing averages, I'm going to do a box plot. And so here I've only got three bins to work with, three buckets, and I can see like the median behaves very similar to what we would have on excuse me, what we would have for our data. And so here I can see that the bins are not in proper order. Is that right? Yeah, the bins are not in proper order, because if they were in proper order, they would increase from left to right. I didn't catch that until just now. All right, so here, if this was proper order, this would be on the far left, then the middle, and far right. And how we like to use this, why this is important, is that I can check to see not only is the central tendency, the median, matched up, but do I have more variability? And so something you also want to consider before you launch a model is how wild are your predictions. If they're, you may be getting the averages close by, and you can actually even get a decent, mean squared error or mean absolute error, but still have like crazy variance in your predictions. And if you have crazy variance, well, you want to do something about it. This plot helps me identify what regions of my data are having problems. And so if I can at least identify that, I have somewhere to go to try and fix it. Now I'm going to do the same thing, but this time I'm basing it off of vision tiles. And so now this is going to be very similar to the lines that we had before. So if we consider the box plot middle lines, that is going to be the median. And so instead of mean, we have medians if we kind of visualize lines on the two types of boxes, but we also can see the spread. So if I had perfect models, the boxes would be mirror images of each other. Let me scroll up. If I had perfect models, these two boxes would be mirrors of each other. These two would be mirrors of each other, mirrors of each other, mirrors of each other, and so on. And so now I can look and I can see that in each of the buckets, I have, substantially more variation in my predicted values than I have in my actual target variable. And that's normal. That's how it's going to play out most of the time. If I'm worried about, performance in particular regions of the data, this gives me like here, this is kind of wide, but then again, when we get the far left and far right, things will tend to be wider than otherwise. So here, I'm not seeing any major red flags. I can see that I've got some skewness going on. so that, if I need to dig deeper, this, is giving me, a flashlight to start, walking through the dark. All right. So model quality is super important. It's more important than the structure of your model. The quality of the output. It's not as sexy to talk about. It's more sexy than like data prep by far. But you should put more emphasis on the quality of your outputs than on the slick algorithms that you're running to be able to fit your model. When I start talking to people, if I hear them talk about like all these different algorithms, this is like maybe somebody's looking for a job, maybe they want to impress me for some reason, they want to talk big. I'll listen to them, and if I don't hear anything that's about data prep and model quality, then I don't really. I know that they haven't had to go through the struggles of truly building a model in a difficult situation. Model quality is something that we have to always think about, and that's why I'm putting it early in our course to make sure. I want you to always think quality model, even if I'm not even ready to evaluate it. I always want the quality on every single step. All right, so here's your homework assignment. Basically, take the data that you've already data prepared for regression, build a simple a multiple linear regression model, and then just run through the stuff that I've presented to you, and tell me what you see. Try to get a feel for it. At first, you're gonna feel uncomfortable. You're gonna be like, "Wow, I have no idea what a vision tile plot is. I don't understand why I'm looking at box plots." Especially people coming from like psychology, anthropology, sociology who take my class, they're gonna feel uncomfortable with box plots. Well, now is a great time to learn it. Start working with it, start getting comfortable with it. The more you look at it, the more you'll feel comfortable, the more you'll be able to use it, the more powerful you are. All right, well, that's all I've got for you. Life is short. Do math.